Hello everyone, welcome to VCIA training course. Before we begin the topic, I'd like to briefly introduce the background and purpose of this training. With the rapid development of the optical network, we are faced with increasing challenges and opportunities. To better adapt to these changes and enhance our professional capabilities and competitiveness, we have specifically organized this training. This training will focus on access network. Through detailed yet easy to understand explanations, we aim to help you master the basic knowledge of access networks, laying a foundation for future maintenance work. Now, let's officially begin today's training content. This training mainly includes the following two parts: Access Network Overview and Network Basics. First, let's move on to the first part of our training: Access Network Overview. The access network in the telecommunication network is located at the edge of the network and is responsible for accessing and converging various services of end users. Wired communication access has a long history in telecommunication network and has played an important role. In terms of technology evolution, the access bandwidth increases with the service requirements, from pure narrowband voice access to XDSL, coaxial cable broadband access, and then to optical access. After completing this part of the training, you should achieve the following objectives. First, describes what is access network. Second, describe the evolution background of access network. I'm sure you're all familiar with the term access network. But what does it exactly mean? Let's take a look at the definition of it. It is defined by ITUT that an access network is an implementation system that consists of a series of transmission entities, such as line facilities and transmission facilities, between a service node interface and a user network interface, and provides required bearer capabilities for providing telecommunications services. In this picture, the left part belongs to the user network interface, and in the right part, it is the service node interface, while in the middle, that is the access network we are talking about. Let's use a more detailed network topology diagram to introduce the components of an access network. The access network refers to all the machines and line devices between the local switch and the user terminal. The access network is directly connected to a large number of users and various application systems, and provides various services for users through various transmission media. The three most common access networks are Radio Access Network, Wired Broadband Access Network, and PTSN Network. With the integration of the Internet into our daily lives, people are no longer satisfied with simply surfing the Internet, and their network requirements have grown increasingly varied. The application scenarios from simple web browsing to online games, to HD online games, and then to 4K videos, The access network has been changed from a single voice service at the beginning to triple play now. Triple play means the integration of telecommunications networks, cable TV networks, and the Internet. Of course, in the face of the challenge of increasingly growing and complex user demands, the access network technology has also made upgrades too. From the beginning, the wired access technology support only XDSL, then later HFC, PLC, and twisted pair media. And now it has evolved to optical access. In the wireless access part, its technology also make a development from wireless 3G to now 4G and 5G. And Wi-Fi upgraded from Wi-Fi 4, Wi-Fi 5 to now Wi-Fi 6. Access technologies are also developing in the direction of larger bandwidth and faster speed. This is a typical PON device link diagram. As we can see, at the top are various cloud services, including the Internet, VoIP, CATV, and so on. Below the top there is OLTs, which are used to transmit these services and manage ONUS. Below the OLTs are ONUS, which are used for FTTH, fiber to the home, FTTB, fiber to the building, and FTTO, fiber to the office. Of course, there are also other application scenarios, such as schools, by connecting to ONUS. Other network devices like computer, smartphone, and fax machine in these buildings can achieve interconnection with the cloud and other networks. Next, let's talk about the second part, network basics. Data communication is a network constructed by various devices, such as routers, switches, firewalls, load balancers, IDS or IPS, and VPN servers. The basic function of the network is to realize data communication between different nodes. In network transmission, MAC address is indispensable, and the way to get MAC, so-called Argentine pesos protocol. Understand the working process of the Argentine pesos protocol. Role of gateway. The function of IP address. It would be easier to understand how data forwarding in network. After completing this part of the training, you should achieve the following objectives. First, understand the concepts of IP address. Second, understand how ARP works. Third, describe how gateway works. Last, describe how data is forwarded. Let's first focus on what is data communication. According to the communication protocol, the transmission technology is used to transfer data information between functional units, so as to realize the information interaction between different devices. The data communication should consist of 5 parts: sender, receiver, medium, protocol, and message. Next, let's take a look at what are the characteristics of the data communication. Please notice that there is no unique link between the two communicating devices. As we can see in this picture, there are 2 packets that are sent from PC1 to PC2, and they are transmitted in 2 different links. In the packet switching, Each packet has a destination address, source address, error control information, and has the ability to find the destination on its own. In this procedure, IP is the most important. If PC1 don't know the IP of PC2, the data communication will not be established. So what is IP address and why it is so useful? Here is the description. An LP address uniquely identifies a network device and consists of 32 binary bits, and the LP address is displayed in dotted decimal notation. As we can see, the IP 192.168.1.1 decimal notation is like this. The LP address is divided into two parts: network address and host address. Let's look at this example too. If the mask is 255.255.255.0, then 192.168.1 is the network address, and the last number is host address. The LP address is a 4-byte, 32-bit binary number in dotted decimal notation. Please pay attention to the example below. The IP 171.17.1.1 can be translated to 32-bit binary number like this. Here is the classification of LP address. As we can see, different range of IP is divided into different class. IPv4 address are divided into 5 types: A, B, C, D, and E. The network number of each type of address is different. Class A, Class B, and Class C address are assignable IP address, and the number of networks and hosts supported by each type of address is different. For example, Class A address can support 126 networks, and each network supports 2 to the power of 24 host addresses. Class D address are multicast address. After a host receives a packet with a Class D address as the destination, and the host is a member of the multicast group, it will receive and process the packet. Now let's move on to the next section. The subnet mask. The subnet mask use masking to distinguish the network part from the host part. So do the mask and LP address are expressed in the same way. In the mask, 1 indicates the network bit, while 0 indicates the host. The subnet mask consists of a series of 1 and a series of 0. 1 indicates the network bits. 0 indicates the host bits. Let's take an example. Right here is 3 network address and its subnet mask. IP address and subnet mask is in decimal form, which can be converted into a 32-bit binary string composed of 0 and 1. Here we had converted IP address and subnet mask into binary string. Then, need to perform a logical AND operation between the binary string of the IP address and the subnet mask. And result will be the network address. So, the top 2 network address is same. so they are in same network. The below one network address is different, so they are not in same network. Apart from the previous parts, this section is also very important. MAC address. The MAC address consists of two parts. The first 24 digits represent the supplier code, which is managed and assigned by IEEE. The remaining 24-bit is assigned by the manufacturer. For example, one of the first 24 digits of MAC address of VSOL network products are 0x8014A8. Following, we will talk about ARP protocol. When a network device has data to send to another network device, it must know the another device's network layer address. That is, IP address. The IP address is provided by the network layer. But only the IP address is not enough. The destination MAC address must also be included. Therefore, the sender must also obtain the destination MAC address. The process of obtaining the destination MAC address through the destination IP address is implemented by the ARP Address Resolution Protocol. ARP protocol is a Layer 2 protocol, which is a fundamental protocol in computer networking that serves the purpose of mapping an IP address to a physical machine address, such as a MAC address. This process allows devices within the same network to communicate with each other by resolving the Layer 3 IP addresses to Layer 2 MAC addresses. ARP packets cannot traverse routers and cannot be forwarded to other broadcast domains. ARP implements dynamic mapping between LP address and MAC address. That is, MAC address are obtained based on known LP address. Let's explain ARP protocol with an example. In this example, left side computer with IP 192.168.6.78 wants to communicate with the computer IP 192.168.6.3 on the right, but it doesn't know the MAC address of 192.168.6.3. So 6.78 broadcast ARP in its broadcast domains, asking who has 192.168.6.3. Then as soon as 6.3 get this ARP, it will reply with its IP and MAC address. Here attach capture of how ARP works. In the previous example, the two devices were on the same network. But what about the two devices are on different network? How would the communication proceed? Let's take a look at the important device that connects different network. Gateway. Gateway is a device that forward data packets to different network. Before the PC sends data, it will first check whether the destination IP is on the same network as itself. If in the same network, it will check the ARP table. if the ARP table has a MAC address corresponding to the IP, it will send the data to that device. If the MAC address is not found in the ARP table, an ARP request will be sent to try to obtain the MAC address corresponding to the IP. If in a different network, it will send data to the gateway. If there is no MAC address of the gateway, we'll get it through ARP. In the last 3 parts introduction, we have learned about what IP address is, how ARP works, and what gateway is. But these are just at a basic level. I am very sure that you are really curious about how data is forwarded in practical application. Data can be transmitted within the same network, or between different networks. And the data forwarding principles of the two are basically the same. Next, I will use 2 examples to explain the process of data transmission between different networks and same network. Let's take this as an example. PCA and PCB are in the same network. When A tries to ping B, A will check its ARP table first. If there is no PCB's IP and MAC address in PCA's MAC ARP table, PCA will send ARP, which requesting the MAC of IP 192.168.0.100. When PCB receives this ARP request, it will reply with ARP2. The source MAC of the ARP from PCB will be PCB's MAC, and the destination MAC will be PCA's MAC. As soon as PCA get the reply, PCA will record PCB's source MAC as the IP 192.168.0.100's MAC in its ARP table. After that, PCA can send ICMP packet to the PCB now. In this situation, PCA and PCB are in the same network. But what about they are in different network? Now let's take a look at this different network situation. Same like before, we will use a real example. As we can see in this picture, PCA and server A are not in the same network. And now, PCA is trying to send data to server A. Let's see how data being forwarded in this case. Firstly, PCA must have a route to the destination. Each PC maintains its own routing table entries. PCA needs to check whether it can reach the destination before sending data. This process is completed by finding a route. In this example, PCA has a route to any network, and the data it sends to other networks will be forwarded to the next hop through the interface with IP address 10.1.1.1, which its gateway is 10.1.1.254. Actually, all router can be default gateway, and if one device want to communicate with other device in other network, then it has to go through its default gateway first. In this example, PCA's network is 10.1.1.0, while server A is in network 172.16.0.100. 1.10.0. So if PC A want to forward data to server A, then PC A need to transmit data to its default gateway 10.1.1.254 first. Then the gateway will help transmit to server A. So how does the data transmit between PC A and its default gateway? What is the procedure? Firstly, PC A will find the next hop MAC address through the ARP table. If the MAC address table entry of the gateway is not found in the ARP table, PC A will obtain the MAC address of the gateway by sending an ARP request. In this example, PC A already knows the MAC address of default gateway 10.1.1.254. So when PC A want to send data to the PCB in other network, PC A will send data to default gateway directly first. And when PC A sends data to the Ethernet, all network devices in this network will receive the frame. After the device receives the frame, it will check the destination MAC address in the frame. If the destination MAC address in the frame is different from its own MAC address, the device will discard the frame, and if it is the same, it will continue processing. So in this case, RTA received the packet, and the destination MAC address is itself, so RTA will continue to forward the packet. PCB received the packet, and the destination MAC address isn't itself, so PCB will drop the packet. After RTA receives this data message, the network layer will process the message. RTA checks the routing table according to the destination IP address to determine whether it can forward the data packet to the destination. And now RTA found out that he can forward data to RTB. So it will forward the packet to RTB. The header of the frame will contain new source MAC address RTA and destination MAC address RTB. And if the current network device does not know the MAC address of the next hop, it will use ARP to obtain it. After RTB received the packet, RTB will use the MAC of server A as the destination MAC to continue forwarding. After server A receives the data frame, it finds that the destination MAC is its own MAC, so it will continue to process the data frame. Server B receives the data frame and finds that the destination MAC is not its MAC, so it will drop it. That's all for this course. Thank you for your attention and listening. We hope this presentation was useful. If you have any further inquiries, please do not hesitate to contact us. There are more courses coming up. Please follow us. Have a nice day. See you.